All right, so just kind of summarizing what we know so far, right? We know that the degree of a polynomial is n, which is its highest power. And we know that a polynomial that is of degree n has at most n zeros and real zeros or x-intercepts. We're going to talk about complex zeros later. And at most n minus 1 turning points. And we'll remind you that turning points are also our relative mins and maxes. Okay, so example here. So we've got a polynomial here. We want to know what's the max number of zeros, x-intercepts, and turning points. So we're going to look at this one and say, what's our highest power of x? It is 6, right? So our max number of real zeros is 6. Our max number of x-intercepts, that's the same thing, also 6. And our maximum number of turning points is 5. Now, looking at this before we look at the graph, we know that our long run behavior, or our end behavior, same thing, it's even, so they're going to go in the same direction, but it's been reflected. That negative sign here is going to make it reflect. So we're looking at something like that. So as x goes to negative infinity, y goes to negative infinity, and as x goes to positive infinity, y goes to negative infinity. They're going in the same direction, and it is down. Okay. Now, when you actually plug this into GeoGebra, you're going to find that it actually only has 2 zeros, 2 real zeros, 2 x-intercepts, and only 1 turning point. So remember that the degree is only giving the maximum number, not the exact number, right? This one has only 1 turning point. It is the y-intercept at 3. Okay, let's see about a second example. Well, let's look at the process. Okay, so in this problem, because we don't know how to factor a degree 6 polynomial just yet, we're having to leave that for the moment. Okay, so we're going to spend 5.4, 5.5, 5.6 talking a little bit more about, hey, how do we do that factoring? How do we figure out what those zeros are? Okay, oops. So our process here, though, to graph a polynomial, we're going to use our leading term test to determine our long run behavior. We're going to find the zeros of the function by solving f of x equals 0. So remember, any real zeros are x-intercepts. For right now, it's generally going to mean you're being given it in factored form or something that we already know how to factor through basic factoring. We're going to find the y-intercept with f of 0, and then we're going to consider the multiplicity of those zeros to check if the graph crosses or if it is tangent, bounces off the x-axis. Okay, so, and then if you need to, you can use the x-intercepts to kind of divide the x-axis into intervals and choose a test point in each part to determine the sign in that interval, like we did way back in chapter 2 with polynomial inequalities. Okay. So for instance, we've got this one. It's in factored form, thankfully. And we want to know, the usual questions here. There we go. So what do we have? We've got the first question up. Well, what's the degree of this polynomial, right? So we're going to look at this and say, okay, well, this part, if I multiply this out, I would get x squared and then some lower order terms. And if I multiplied this part out, I would get x cubed and some lower order terms, right? So the highest power possible is going to be x to the 5th, which means this is a 5th degree polynomial, right? What's our domain? All real numbers. It's a polynomial. It's always all real numbers, right? What's our long run behavior? Well, we know it's odd, so we know it's going to look some version of a cubic, right? Has it been reflected? No, because if we multiply these out, we multiply out the squared, our highest power is just straight up x squared, the x minus 1 cubed, our highest power is going to be straight up x cubed. So our long run behavior, it's not reflected. So we're looking as x goes to negative infinity, y goes to negative infinity. And I know there's something else coming up here. So as x goes to positive infinity, y goes to positive infinity. So we know it's doing this. All right, what are zeros? Well, we know this is we know x plus 3 equals 0. So one of our zeros will be negative 3. And that has a multiplicity, which I'm just going to write m, of 2. And then we've got x minus 1 equals 0. So x will equal 1. And that has a multiplicity of 3. So if there's our zeros. And we know multiplicity 2 is going to basically bounce off the x-axis, right? It's tangent, which means it touches but doesn't cross. And a multiplicity of 3 is going to cross, but we're going to have that concavity change there, like this. All right? And, you know, on a paper test, I would be looking for those concavity differences if I asked you to sketch one of these things, okay? Now this is not going to be to scale, but we'll get the idea here. Sorry, there, we'll do that. And we're just kind of connecting to our long run behavior. Okay, so turning points on this one, we actually only have, we have 2, right? We have, we'll do highlighter, right? So there's a turning point here, and there's some sort of turning point there. There's a minimum there, maximum at negative 3. So we had a max of 4. We actually only have 2 turning points. One at x equals negative 3, and one at, we're just going to have to guess here. It's maybe negative 1 or negative 2 or so. And which we could find that by graphing and using GeoGebra, or if you continue on to calculus, you can find out exactly where those turning points are. All right, and we know that this is not to scale because f of 0 on this one is going to be negative 9 if we plug that in. So the scale, vertical scale, is not correct on this thing. But we do have a good idea of what the graph looks like. And in fact, we can go pull up GeoGebra, erase this one, and we're going to say y equals x plus 3 squared times x minus 1 cubed. And you can see, especially if I zoom a little bit out here, there we go. This looks like what we drew, just like what we drew needed to be vertically stretched quite a bit. Let's pull that back up. There we go, right? So we see, look, we can do that. That looks better, right? So we didn't get our vertical scale right. We knew that that was the case because I wasn't really focused on that. All right, so we'll stop here. We got several more examples to go.